together. Molecules think so too, especially hemoglobin, which is a great example of allostery and cooperative binding. Basically, if something has multiple binding sites, the binding at one site can influence the binding at other sites. This is called cooperativity, and we're going to talk in detail about what it is, how it shows up in hemoglobin, and then prepare you for further in-depth investigation into hemoglobin. Let's start with just a quick review of our binding thermodynamics and concepts. So remember that ligand is just a word for a binding partner. It's a generic umbrella term. We can talk about ligands for all sorts of things, such as ligands for receptors. That's a really common one. And so today what we're going to be talking about mainly is going to be looking at the binding of oxygen to hemoglobin. So oxygen would be our ligand, and it's binding to hemoglobin. No matter what binding partners we're talking about, we can talk about the affinity or the strength of binding in terms of something called the dissociation constant. So the equilibrium dissociation constant, or KD, is basically a measure of how strong the binding is. But it corresponds to kind of like things in the reverse direction. So it's going to end up being the concentration of A at which half of B is bound, meaning that weaker binders are actually going to have a higher KD. They're going to require a higher concentration of A in order for half of B to be bound. So this is an equilibrium constant. It's constant for given conditions, and it comes based on kind of like the intrinsic probabilities that these molecules are going to like bind, so get married and then unbind or get divorced, you can think about. So like the rate constants, K on and K off. And so remember, we could also talk about KD is equal to our K off over our K on. And remember, these are the little k's, so our rate constants, as opposed to our big K, our equilibrium constant. So the KD is going to come from some contribution of the K off and the K on. And what happens is that those intrinsic rate constants are going to kind of make it more likely to bind or unbind, but then how much of it you actually find bound is going to depend on how much of it is around. And so what's going to happen is if we were to measure the proportion of one partner bound over a range of concentrations of the other partner, then what we could do is we could calculate the KD. So let's go ahead and think back about what would happen if we actually want to do this. Let's think about our simplest case. So we're going to talk about simplest case. One binding site. So we're going to have a constant low concentration of B. And we're going to increase the concentration of A. And then we're going to go and we're going to measure what proportion of B is bound. Remember, we can also write this as theta B. Okay, so what's going to happen if there is no A around? Well, if there's no A around, then none of B is going to be bound to A. And so we have a point down here. But what if there's a lot of A around? Well, now all of your B is going to be bound and you're going to be up here. And you're going to be up here for a while because if you add more than you have like sites, you're going to reach saturation. So you're going to plateau out when all of it is bound, or at least all of how much of it is functional is going to be bound. So in the middle, what's going to happen is you're going to bind. As you bind, you're going to be taking away a little bit of you're going to be like adding competition. There's less of the partner around. And so what's going to happen is you're kind of going to get this hyperbolic curve. So this is what happens if we have a single binding site. So this point that we plateau, we can call this the B max, so the maximum binding. And we can also look at the half B max, so half of the maximum binding. And the value of doing that is then if we go down, and we look at the concentration, well, this is going to be our KD, because remember, that's the concentration of one partner at which half of the other partner is bound. So this allows us to find the KD. Remember that if we had a weaker binder, it's going to have a curve that's shifted to the right, meaning that you need more of the one partner in order for half of the other to be bound. And if it were the other way around, it'd be shifted to the left. And so note that this figure is going to be drawn the opposite way. So I have concentration of B on the bottom and then A on the right, on the y-axis. It's not to confuse you, and it's just because that's what I had. But it also helps remind us that basically we can define this in terms of either of the partners, because we kind of just arbitrarily say which is A and which is B. But now let's go ahead and let's look at a more complicated case. What if we have multiple binding sites? So we have a single molecule with multiple binding sites. How are we going to tackle this? Well, let's start by thinking of an analogy. Let's think back to our dating scenario or our marriage scenario, where we have people that can get married and people that can get divorced. And then we can go and we can look and see how many of them are married and how many of them are divorced. So let's think about a car containing Sally and Jane. So we'll think of them as like a single molecule with two binding sites. So we'll take that car with Sally and Jane, and we want to see, okay, well, how many of them are bound? What proportion of them are bound? And so what we can think of that is basically a molecule with what proportion of its binding sites are bound. Well, this will depend on whether the marriages are kind of independent of one another. If Sally were to get married, would that influence Jane's chance of getting married? If not, then we just have a simple case, just like before, where what's going to happen is you're going to have that simple sigmoidal curve. You're just going to have your B max. B max is going to be equal to of two binding sites, two bounds, instead of one bound. But we can still go and we can calculate our half B max, and we can go and we can calculate our KD. And remember that KD is going to come from like the intrinsic affinity for binding to that first site, or the intrinsic probability that one of these friends is going to get married. But now let's think about what would happen if the marriage of one of the friends influenced the marriage of the other. Say Sally gets married and she has this great experience and she's got all these like wedding highs, and she's this is going to make Jane want to get married more. So Jane is going to have a higher affinity. So what's going to happen is that, well, for the first marriage, for Sally to get married, that isn't going to be influenced by anything. And so you're going to get the same KD. But then once Sally gets married, well, now Jane has a higher probability of marrying. And so what you're going to get is you're going to get this sigmoidal curve. But now let's think about the opposite direction. What if we have a situation where Sally gets married and she has this horrible experience and she's telling Jane how awful it is, and this makes Jane less likely to get married? Now what's going to happen is basically you still have that same original KD that you'll reach, but you're kind of going to get a lower plateau, or at least a slower rise. So it would take a higher concentration in order for all of it to get bound. And so basically what we see is that we can think about three scenarios. We can think about our normal scenario, which we'll call non-cooperative binding. And this is where the binding to one site doesn't impact the others. But then we have the scenario where we have what we call positively cooperative binding, where the binding of one partner positively influences the binding of the other. So the marriage of Sally makes Jane more likely to get married. And then we have the scenario where we have negative cooperativity, where the binding of one partner decreases the likelihood the other partner will get bound. And so this is when we have Sally get married and makes Jane less likely to get married. So we have these key terms that you need to know. Cooperative binding is when the binding of one molecule of a ligand affects binding of subsequent molecules of a ligand. This can be positive cooperativity, where binding of the first increases binding affinity of the next, or it could be negative cooperativity, where binding of the first decreases binding affinity of the next. Most commonly, we're going to be talking about positive cooperativity, and we're going to look at how we can see this in action in hemoglobin, which is the protein that carries oxygen through our blood. Before we get too far into it, though, I want to make sure that we're all on the same page about what we mean by having like a sigmoidal plot. That's talking about if we're on a linear scale. So remember back to our video on our affinity and KD, and how we talked about we can basically, if we have an experiment, we might get a lot of points crunched up onto near your y-axis if you're doing like a serial dilution. So what you have here is you have on the x-axis, you have the concentration of one of the binding partners.
And then on the y-axis, you have the fraction of the other binding partner that's bound. And you can see that I have a lot of points squished up through here, which makes it hard to see. So often what we do is we plot these on a log scale. And so basically we're just kind of spreading out the scale, spreading out that smaller point, the points near the origin. And this is going to make it easier to see our points, but it's also going to make that normal non-cooperative plot look like it had a sigmoidal shape. And so you always need to check your x-axis because even non-cooperative binding looks sigmoidal on a semilog plot. So semilog because we're taking the log of the x-axis, but not the y-axis. So basically check your x-axis. If you see a sigmoidal curve on a linear axis, that will indicate cooperative binding or just really poor experimental skills. But if you see a sigmoidal curve on a log scale, well, that doesn't really tell you anything. But if you do have cooperative binding, you'll still see like a sharper sigmoidal curve. So now let's go and let's look at an actual example, a really, really crucial example, the example of hemoglobin, which carries oxygen through the blood. So hemoglobin is made up of 4 separately made protein chains. So what do we call this when we have something like this? There's a term that we use that we've been talking about. This is going to be an example of a multimer. So basically, a multimer is when you have multiple chains in a protein, and the interactions between those chains, we can think of them as representing quaternary structure. So hemoglobin is a great example of what we call a heterotetramer. So tetramer meaning tetra, meaning 4, and hetero because it's going to have different subunits. It actually has 2 copies of 2 subunits. So basically the adult version has 2 beta subunits and 2 alpha subunits. And when we talk about fetal hemoglobin, that's going to have gamma subunits. Each of those subunits is going to hold onto a heme group. So heme is one of those like cofactors. It's a prosthetic group. It's really tightly held. This is a non-protein part that's going to be kind of give hemoglobin the extra superpowers that you can't get from protein alone. And so these heme molecules in their center, they're going to bind to iron, and that iron is then going to bind to oxygen, and this is going to help transport oxygen throughout the blood. So that was what it actually looked like, but for a little bit, we're going to draw it like this. And remember that in that figure, I drew it in I colored it with slightly different shades of blue and pink so that you could tell apart the different chains, but the A's and B's are just copies. Okay, so now let's look and see what happens. So we said we had those 4 binding sites. We had those 4 hemes, and each of those hemes could bind oxygen. We're going to see that hemoglobin is going to have positive cooperativity, which means that once you get that first binding of oxygen, and so remember that first binding is just going to depend on the original, like the affinity. And so that's going to also, the speed of that binding is going to depend on how much oxygen is around, and then also hemoglobin's oxygen affinity. Which is going to depend on pH and stuff like this. So we'll talk about how the Bohr effect, how the pH can influence the binding affinity. But for now, just know that basically based on the intrinsic properties of hemoglobin and its environment, you're going to have some probabilities of the initial oxygen binding. And now we have to think about what happens once that initial oxygen binds. Do we have a situation like where Sally and Jane don't care if the other one gets married, it doesn't influence them? Or do we have a situation where it does influence them either positively or negatively? Well, in the case of hemoglobin, it influences things positively. So once that initial oxygen binds, well, now those other oxygens are going to snap on, those other oxygens are going to get grabbed right up. So basically you increase the affinity of those later sites. Going the other direction, however, what if we let go, talking about the ability to bind and the ability to unbind, and we can't really uncouple the two. So what this means is that that same cooperativity that's going to make it so that one of them is going to cause the other sites to bind faster is also going to make it so that if one of the sites unbinds, the other ones are going to more quickly unbind. There are a couple of different models as to how this actually happens, like whether the binding of one site makes it just more likely for all the other sites to bind, or whether it's kind of like sequential, where one is directly influencing the one next to it, but not all of them, and that sort of thing. So there are these couple different models you might see, but don't worry about knowing all the details of these. Just know that there are different models, and you're going to see some different proportions of sites that are bound or unbound in all those different molecules if you were to go and look. So now let's talk about what's actually causing this cooperativity at like the molecular level, because that's where I love to think. Basically, we can talk about allosteric effects. This is where something happening at one place of a molecule affects another part of the molecule. So when we think about this word root allo is going to mean other. So something's happening at some other place that's going to affect this place. This is often going to be some sort of conformational change. So remember that a conformation is just kind of like a shape, and a conformational change is then just a molecular shape shift. So these are interconvertible, and they often happen in response to binding something, and that's exactly what we're going to see here. So some key terms that we're going to need to know are allostery, which we just talked about, where something that happens at one location, such as the binding of a ligand to a protein, is going to affect what happens somewhere else in that molecule, such as the binding of a second ligand to that protein. Now, those ligands that cause the allostery that affects the other binding, so if you have something bind and then it makes some allosteric effect that makes the other site more or less likely to bind, we call that initial thing that bound a modulator. And so this modulator can be negative, it would decrease the affinity of the next one, or it could be positive, which would increase the affinity of the next one. So let's think about our case of oxygen. What type of modulator was oxygen? Oxygen was a positive modulator because it was going to increase the affinity of further oxygen's binding. So we got positive cooperativity thanks to having a positive modulator. Oxygen was also an example of a homotropic modulator. So homo meaning same, and so basically this means that we have a modulator that's going to affect the binding of the same ligand. So in this case, our modulator was a ligand. We're just talking about multiple copies of that same molecule binding. So that first oxygen was going to act as a homotropic positive modulator. It was going to be the same ligand as the next ligand that it affects. It's just a different copy of it. And it's going to positively affect the binding of that second ligand or of the next ligand in line. So remember, with hemoglobin, we actually have 4 sites, but we can find that basically once one binds, then the others can kind of like follow suit and promote the binding of the rest. We also have heterotropic modulators. So that would be different. So this is when your modulator is going to affect binding of a different ligand. So in this case, your modulator is not your same as your ligand. Now that we know these terms, let's go back and look at what's happening molecularly. So in hemoglobin, we basically have these 2 states. We have the state where oxygen is bound, and then the state where oxygen is not bound. We can refer to these as the taut and relaxed forms, or T and R. So this taut form, this is going to be your deoxy form, because you don't have oxygen. And then this relaxed form, this is going to be your oxy form. And so why do we call it taut and relaxed? Well, if we look at where those kind of like shaded circles are, it's kind of hard to see here, but we'll get into it in more detail. Basically, you have these interactions between the subunits. You have more salt bridges, more of those ionic bonds that are going to help kind of certify it. But they're going to certify it in this version with a bigger hole in the center. So this bigger central channel. In the R form, well, here you're going to have a smaller central channel, and you're going to have weaker interactions between like those subunits. Those salt bridges aren't going to be as strong, and so we call it like relaxed. Now, why do we get this form? What's going to happen is basically the binding of oxygen is going to pull on that heme group and kind of like flatten it. And well, there's a histidine on the other side that is kind of making interactions with that iron. And therefore this heme is then, this histidine is then going to get shifted as well. And this is going to kind of relay an effect throughout the rest of the protein. Remember what we call that sort of thing? Yeah, we call it an allosteric effect. We're having a conformational change that's being kind of relayed from one part of the molecule to the other part of the molecule. And what this is going to do is it's going to cause all those interactions to change. Because remember, the protein is like, it's got this orientation where everything's kind of lined up for these nice little bonds. And then if you shift everything, then you have to form new bonds. And so you end up with stabilizing in a different conformation. So what happens is you get this T state where it's stabilized in a conformation that has a low affinity for oxygen, or you're stabilized in an R state, which has a higher affinity for oxygen. So this helps us understand how if we have binding of oxygen at one site, it's kind of going to shift the whole protein and stabilize it in that site that has a higher affinity for oxygen, that R state. So the initial binding is still going to be hard. It's still going to be determined by that kind of like intrinsic rate of that site binding. But then once you bind that site, it kind of shifts the other sites into, it shifts the whole molecule into a version that's more likely to then go and bind oxygen. What this means in practice is that you end up getting one of those sigmoidal curves. So this is showing us positive cooperativity. Now, when you're talking about hemoglobin and binding oxygen, when we're talking about concentrations of gases, we often talk about them in terms of partial pressure. So basically, the PO2, that's just the partial pressure of oxygen. So you can think of it as just oxygen concentration. And then if we look at hemoglobin saturation, remember that here RB max is actually going to correspond to 4 sites being bound. And then we can kind of look down and we can go and we can see instead of what we call the KD, we kind of call it like the P50. This is going to be our P50. So that's the partial pressure of oxygen at which half of the hemoglobin sites are bound. So remember, this is sites. So it would be like 4 sites bound, 4 bound. And down here, you would have 0 bounds. Remember that because one site binds, what influences the next site's binding, you're going to have it so that you're going to have more of the ones with none or more of the ones with all, but less of the ones with the intermediate. So you're going to get a mix though. So when you have a sigmoidal curve like this, one of the consequences is that when you're in the mid-range, small differences in the PO2 can make a really big difference. And this has important biological consequences. Let's think about why. Remember that we're talking about the concentration of oxygen here, and the concentration of oxygen is going to vary at different places in your body, which means that the relative amount of saturation of your hemoglobin is also going to vary in different places in your body. If we think about the lungs, there's going to be a high concentration of oxygen. But if we think about our legs, well, there's going to be a low concentration of oxygen there. So ideally, we want some situation where at the high concentration of oxygen, we can kind of just grab it all up. And at the low concentrations, we'll kind of just dump it all out. And so what happens is that because we have that cooperative binding, this is what's going to happen. Go and think about what would happen in your tissues or in your lungs. So remember that how those differ is going to be in the concentration of oxygen. And the concentration of oxygen is going to influence both that initial binding as well as then once you get that initial binding, the subsequent binding. And so if you have a high concentration of oxygen, then you're going to be stabilized in the oxygen-loving R form. And if you have a low concentration of oxygen, you'll be stabilized in the not-so-loving T form. And this is why we get the sigmoidal curve. But in our lungs, what's going to happen is we're going to have that R form stabilized. And we're going to have this high oxygen concentration. If we were to go and we were to look and see, okay, well, how much of it would be bound? Almost all of it's going to be bound in our lungs. But now let's go and let's look at what's happening in our tissues. Well, in our tissues, you can see that there's kind of this range of concentrations. So in our tissues, we're kind of have a situation where we're going to be somewhere in this range, where we're going to have somewhere around maybe like 50% or so of the hemoglobin is going to be bound. So we're going to have a big change. So delta Y is going to be very big. Okay, but now let's think about if we didn't have cooperativity. So what if we were stuck in that low affinity state? So what if we were stuck in T all the time? Well, now what's going to happen is in our lungs, well, first of all, we're not going to have very efficient loading. You can see that even at these high oxygen concentrations, we're still only about 50% of it actually being saturated. But if we look at basically in our lungs, we have something like this. So now our lungs are more similar to what our tissues were before, and our tissues are going to be all the way down here. So you can see that also we're getting a smaller change in our delta Y. So we're getting a smaller difference between the two, and we're also getting a smaller total. Now, what would happen if we were stabilized in that high affinity state? So basically the high affinity state, this would be kind of like stuck in R all the time. Well, now what's going to happen is that if we look at both our lungs and in our tissues, they're both going to be almost completely bound, which means that you're not releasing any, you're not giving those toes oxygen. So we want high affinity in our lungs so we can pick up the oxygen, but we need that low affinity in our toes so we can release that oxygen. And having this cooperative binding is going to allow us to do that. It's going to give us this sigmoidal binding curve where we have this transition state where we then able to release the oxygen efficiently. And when you're in that range, small changes in the oxygen concentration can make a really big difference. So this is, if you make that initial binding more likely, you can make full binding more likely. And this is why if you like add supplemental oxygen, you can often help people out really, really quickly if they're don't have enough oxygen. There's this thing called the Hill equation that tries to quantify the extent and direction of cooperativity. And I don't need you to know the details about where this comes from or anything like that. Know that your textbook goes into it more if you want more information. What I do want you to know is that you'll see this written as like NH for the Hill coefficient. That corresponds to, like, the N is the theoretical number of sites. And then the H is telling you the Hill coefficient. If that Hill coefficient is 1, that's saying there's no cooperativity. Or sometimes you might see something that's like really close to 1. That's just like experimental error or overfitting or something. If you see something that's significantly more than 1, that's going to mean you have positive cooperativity. And if it's less than 1, that's going to be negative cooperativity. These are just like theoretical, like maximum and extents and things like this. You will see those values used though, and it can be helpful to try to compare, like if there's a mutation, does that affect cooperativity and things like that. So before we move on, just a quick concept check. Remember, what do we call oxygen in terms of the effects it has on hemoglobin? Right, it's a positive modulator. So basically, once oxygen binds, it's going to make it higher affinity for the next oxygen site binding. We call it a homotropic modulator because it's the same, it's affecting one copy of oxygen is affecting the binding of another copy of oxygen. So it's affecting the binding of another copy of that same ligand. But now let's look at an example of an heterotropic modulator. And in particular, we're going to look at a heterotropic negative modulator. So we're going all the way in the other direction. We're going to be talking about this molecule called 2,3-bisphosphoglyceric acid, or 2,3-BPG. Basically, there's this molecule 1,3-biphosphoglycerate that can kind of get sidetracked and take this alternative route and become like shift to become 2,3-bisphosphoglycerate. Bottom line, when your cells are undergoing glycolysis, they create this some of this 2,3-BPG. So we're going to be making this in our tissues. Why does this matter? Well, this 2,3-BPG is going to act as a negative modulator. So what it's going to do is once it binds to hemoglobin, it's going to reduce the binding affinity of the oxygens. So let's think about why this might be. Let's look at the binding site of 2,3-BPG. It's binding in that central channel of hemoglobin. Remember that central channel is going to be closed tightly in the R state, or it's not like there's no space in there, but there's not really space for BPG. But in the T state, well, now you have a more open central channel, and that's where BPG is going to bind. We can actually go and we can look at the interactions that BPG makes with hemoglobin. So this is from the PDB 101, or I guess the PDB molecule of the month. They have some cool articles, and this one is on BPG and other things about hemoglobin. This is showing you the adult hemoglobin, and you can see 2,3-DPG bound in the center. What type of interactions are we seeing displayed here? Right, we're seeing ionic interactions. We're seeing salt bridges. So these are going to be salt bridges. So 2,3-BPG, that phosphate, basically what you have is those phosphate groups are going to be negatively charged. You have in the pocket, in its binding site, you have histidines, you have lysines. What do we call these? Yeah, those are our basic amino acids. Those are going to be the positively charged ones. And so they're going to be able to make these salt bridges, these ionic bonds with the phosphate groups of your 2,3-BPG. And this is going to hold it nice in there. And if we're stabilizing the T state, well, this means that we're stabilizing that state that has a low affinity for oxygen. And so this is going to make it so that BPG is going to cause hemoglobin to have a low affinity for oxygen. So a lot of the effects that we see, a lot of the sigmoidal shape of our curves actually comes from there being this BPG present in our tissues as well. So if we were to look in the absence of BPG, if you were to think about there being no BPG, you actually get more of a hyperbolic curve. So there's not that strong of cooperativity. But if you think of BPG as kind of what it does is when you're in that T state, when you're in that low oxygen state, it can kind of bind in the center and make those interactions that are stabilizing that state and making it harder to go back to that R state. So you're kind of, once you're in those tissues, you have this BPG, you've got the low oxygen. Well, now what's going to happen is you're going to stabilize in this form that's good at dumping out that oxygen so your toes can get it. The more 2,3-BPG you have, the more likely you are to find it in that offloading state, in that T state, the state that has deoxy. It's offloaded the oxygen. And so you don't want that state in your lungs, but you do want that state in your tissues. Now let's think about what we would have in our lungs at sea level or at a high altitude. Well, when we're at sea level, this is what we were talking about before. We've got that really high, we've got like 96, 99%, most of our hemoglobin is going to be bound in our lungs. But then if we go down to our tissue, we saw that basically we were going to be offloading more of it. So we had about a change of about 38%. But now let's think about if we started at a lower oxygen concentration. If we started at a low oxygen concentration and we have that same amount of BPG, well, now what's going to happen is we're going to have a lower proportion of it be bound in at its full capacity, the maximum oxygen we have, we're going to have a lesser amount of it be actually bound. So we're going to have about like 8% less of it. So we'd have something around like 90% bound. And this means that if you still you still release the same amount in your tissue, you still have the same proportion in your tissues as you had before, but now you're starting at a lower value amount. So you have a smaller change. You have less of the oxygen that's actually getting offloaded. One way to counterbalance this is to make more 2,3-BPG. And so if you think about it, you can't change the amount of oxygen that's out there, but you can change how much you're dumping out. So if you have more 2,3-BPG, well, you're going to get slightly less bound when you're at your maximum, but this is okay because we're going to actually have a bigger decrease when we are in our tissues. So we're dumping out more in our tissues. And so overall, we end up with a change of about 37%, similarly to what we had at the lower BPG concentration at sea level. So bottom line, BPG is acting as this negative modulator of binding, and the BPG levels can be modulated. We can make more of it, we can make less of it in order to best suit our body's needs. So how would we classify BPG? BPG is going to be a heterotropic negative modulator. So it's heterotropic because it's different than the ligand that we're talking about. So we're talking about BPG affecting the binding of oxygen. It's affecting it negatively, so we call it a negative modulator. One more cool thing about BPG before we finish is that we also have, as I mentioned before, there's like fetal hemoglobin, which basically it has gamma subunits instead of those beta subunits. And what this means is that it has different affinities for oxygen than the adult hemoglobin. Oh, and note that HbA, that's just the adult hemoglobin, and HbF, that's the fetal hemoglobin. So remember that the fetal hemoglobin is going to have those gamma subunits. And one of the reasons why it has these different affinities is because it actually has a different affinity for BPG. So let's think about what a fetus would need. Well, a fetus would need to have a high affinity for oxygen so that it could take all the oxygen it could get out of the mother's blood. So we're not talking about the situation where we have things at like sea level versus higher elevation, where there's slightly less oxygen in the air. Instead, we're talking about the fetus encountering the mother's blood the mother has taken out a lot of the oxygen. And so we need to have a high affinity for oxygen. So would we want there to be BPG or not found? No, we don't want there to be a lot of BPG. But remember that the BPG is going to be like a byproduct of like metabolism. And so, well, that fetus has to do a lot of metabolism in order to grow and develop. And so you're going to have BPG around, a lot of it. So we need a way to kind of deal with a lot of it being around. And one way that we could do that is by having a lower affinity for it. So fetal hemoglobin has a lower affinity for BPG, and therefore it isn't going to be influenced as much by it. It's actually really cool why this is. So basically, if you look at fetal hemoglobin at what would be the binding site for BPG and compare it to the adult hemoglobin, and again, this is from that same PDB entry. Note that here it's labeled 2,3-DPG because like diphosphoglycerate, but it can also be called biphosphoglycerate. So bi-di, so that's why you see DPG here instead of BPG. But bottom line, what you see is that all these ionic interactions that you have here, well, they're not really possible as easily in the fetal hemoglobin. So what you'll see is that we actually lose the ability to form some of those salt bridges because of amino acid changes. So over here in the adult hemoglobin, we can see that we have this His 143 making a salt bridge with our BPG. If we were to look and try to see if that could form in fetal hemoglobin, well, now we see that we have a serine where that histidine was, so that salt bridge wouldn't be possible. Even for the amino acid residues that were making the bonds that are still conserved between these, like this His2, this lyse 82, basically, and lyse 82, basically, because you're looking at multiple subunits, that's why they're labeled the same, by the way. But what you can see is that you actually are going to have changes in the orientation of the side chains so that they're no longer in position to bind to that BPG. As a result, what's going to happen is that the fetal hemoglobin is basically going to have that high affinity, but the BPG is going to make it so that it lowers the affinity somewhat, so you do get offloading, but not so much as if you had the adult hemoglobin, so you still can grab enough of it when you're at that lower oxygen concentration. To review, the key terms for today are cooperative binding. This is where binding of one molecule of the ligand affects binding of subsequent molecules of the ligand. This can be positive cooperativity, where binding of the first increases binding of the affinity of the next, or negative cooperativity, where binding of the first decreases affinity of the next. So remember, this is like if Sally got married and then that made Jane more likely to get married, that would be positive cooperativity. But if Sally got married and then started talking about how awful marriage was, well, now Jane would be less likely to get married. That would be negative cooperativity. Often cooperativity comes from allosteric effects. So basically allostery is where something that happens at one location of a molecule, such as the binding of a ligand to a protein, affects what happens somewhere else in that molecule, such as the binding of a second copy of that ligand to the protein, or the second ligand, a copy of a different ligand to the protein. We can talk about modulators. These are ligands that cause allostery that affect binding of ligands. So these can be negative, where they decrease the affinity of a ligand, or positive, where they increase the affinity. These can be also classified as homotropic, where you have a modulator affecting binding of the same ligand, so like our oxygen affecting the binding of oxygen, or they can be heterotropic, where a modulator affects binding of a different ligand. So in this case, our modulator isn't just another copy of the ligand. An example of this was our BPG, which is going to act as a heterotropic modulator. More specifically, it's going to act as a negative heterotropic modulator because it's decreasing the binding of oxygen, whereas oxygen acted as a homotropic positive modulator because it was increasing the affinity of the subsequent binding. Don't worry about hill plots. I don't need you to actually go read a hill plot or draw a hill plot by any means. But do know that the slope of the line of a hill plot, that's where we get this term NH. And the value is going to tell you about the extent and direction of cooperativity. If NH equals 1, you don't have cooperativity. The equation kind of just simplifies down to the equation that we've been looking at all this time for our KD. But if you have a NH of greater than 1, you have a positive slope, you have positive cooperativity. If NH is less than 1, you have negative cooperativity. Remember that the NH, the maximum value it can be is the number of sites, but you're never going to find it actually be equal to that number of sites. In terms of number of sites, hemoglobin has 4 of these sites, and they bind cooperatively. So once that first oxygen binds, it makes it more likely for those other ones to bind. And then if one lets go, the others quickly follow. This means that when you're in that middle range, small changes in the oxygen concentration can have a big difference. We saw that this was molecularly based. We could talk about the oxygen kind of pulling on that heme and pulling on the iron and the histidine that was bound to it, and kind of causing all these allosteric changes that are going to stabilize the hemoglobin in this R state, which is going to have a higher affinity for oxygen. You're going to load your oxygen, but then once one of those oxygens is released, then you're going to get stabilized in the top form, the T form, where you have a lower affinity for oxygen. You're unloading in the tissues. In our next lesson, we'll go into more details about the molecular interactions that are actually happening between the subunits and how the Bohr effect explains how changes in pH influence the state of these molecules. Spoiler alert for those that want them, basically they're going to influence those salt bridges that are holding together the T form. Those are dependent on a histidine being protonated, so they need a low pH. So when you have a low pH, such as if you have a lot of carbon dioxide, then that's going to stabilize this unloading form, making it so that you're able to offload even more easily in those tissues where you're depleted and you have that high concentration of CO2.